DeepSeek used NVIDIA Blackwell chips to train its latest AI model and is expected to drop next week. And that's not the only new accusation being leveled against Chinese AI labs.
Chips into China was always very simple. If we sell them older generations of American chips.
What if the future of faster chips isn't smaller, but taller? For decades, engineers squeezed more performance from processors by shrinking transistors. Now Huawei is challenging that formula with something far more radical: logic folding. Instead of keeping logic spread across a flat silicon surface, the company is stacking layers and connecting them vertically, potentially shortening the distance signals have to travel. Huawei says its Kirin 2026 already demonstrates the idea, with 55% higher transistor density and 41% lower power at equivalent performance. But the real gamble comes next. Huawei wants sub-1 micron bonding and 5 GHz speeds by 2031. Could this actually rewrite Moore's law? The next chip breakthrough. For more than half a century, the semiconductor industry had a remarkably effective trick: make things smaller. This idea is usually associated with Moore's law.
To keep achieving Moore's law, chip makers have to make individual chip components smaller. And
the observation that the number of transistors that can be economically packed onto an integrated circuit tends to increase dramatically over time. But modern chip scaling is much more complicated than simply drawing smaller rectangles. A transistor is essentially a tiny electrical switch. Millions or billions of those switches are connected together to perform calculations, store information, and control the movement of data. The problem is that those switches do not operate in isolation. They have to communicate. And on modern chips, that communication can become one of the biggest limitations. Imagine a city filled with billions of tiny factories. Making the factories smaller allows you to fit more of them into the same area. But if the roads connecting those factories remain long and crowded, shrinking the factories does not automatically make the entire city faster. The same thing happens inside a processor. A signal has to move from one transistor or logic gate to another. The longer and more electrically difficult that connection becomes, the more time and energy the signal can require. This is where something called RC delay becomes important. RC does not mean a particular chip component. It refers to the combined effect of resistance and capacitance in an electrical connection. Resistance is the opposition to electrical current. Capacitance is the tendency of a connection to store electrical charge. Put them together, and you get a rough picture of how quickly a wire can respond to a changing signal. Think of it like pushing water through a long, narrow pipe that also has a flexible reservoir attached to it. The pipe resists the flow. The reservoir has to fill and empty. The longer and more complicated the system becomes, the harder it is to change the state quickly. In a chip, that delay matters because a processor cannot simply move on whenever it wants. Some calculations form what engineers call a critical path, the chain of operations that determines how quickly a particular piece of logic can finish. If that path is too slow, the entire circuit has to wait. And this is one reason modern semiconductor scaling has become so difficult. The transistor can become smaller while the overall system stops getting proportionally faster. At the same time, shrinking transistors requires increasingly sophisticated manufacturing equipment. One of the most important technologies in advanced chip production is EUV lithography. EUV stands for extreme ultraviolet.
Think of an EUV machine as the world's most precise printer.
It uses extremely short wavelength ultraviolet light to print extraordinarily fine patterns onto silicon wafers. The equipment required is enormous, expensive, and extraordinarily difficult to build. Huawei and other Chinese semiconductor companies have been restricted from accessing the most advanced foreign semiconductor manufacturing technologies as US-China technology controls tightened. That matters because advanced lithography is one of the major tools used by leading foundries to continue conventional geometric scaling. Companies such as TSMC and Intel are pursuing increasingly advanced transistor architectures and manufacturing processes, while ASML's EUV systems sit at the center of the most advanced lithography supply chain. Huawei therefore faces a strange engineering problem. It still wants more transistors. It still wants faster processors. It still wants better energy efficiency. But it cannot simply assume that the next generation of manufacturing equipment will arrive and solve the problem. So Huawei began asking a different question. What if smaller transistors are only one way of making signals move faster? What if you could attack the distance instead? That is where the Tau scaling law enters the picture. Huawei presented the concept in Shanghai in May 2026, when He Tingbo, a Huawei board member and president of the company's semiconductor business, outlined the company's proposed post-Moore approach. The basic idea is to treat time, the tau in tau, as a fundamental scaling target. Instead of asking only, how small can we make the transistor, engineers can also ask, how much can we reduce the time it takes for the system to do its work? That sounds abstract, but Huawei attached it to a very physical technology. LogicFolding. LogicFolding is where the idea stops sounding like a new slogan and starts becoming an engineering problem. Because Huawei is not simply trying to make the same flat chip smaller, it is trying to fold part of the circuit. And once you do that, the geometry changes completely. The chip architecture has changed. Picture a sheet of paper. On that sheet, you draw a long line connecting point A to point B. Now imagine you have to travel along that line every time you carry a message from A to B. The line is long. The message takes time to travel. Now fold the paper in half. Suddenly, two distant points on the original sheet can sit directly on top of each other. The physical distance between them has collapsed. The drawing did not become smaller. The paper simply changed shape. That is the intuition behind logic folding. Obviously, a semiconductor is vastly more complicated than folded paper. But the analogy captures the essential idea. Huawei is taking logic that would traditionally be arranged across a mostly planar silicon surface and distributing portions of that logic across vertically stacked active layers. The two layers are then connected through hybrid bonding. Hybrid bonding is a method of joining two semiconductor surfaces directly.
Hybrid bonding is what I would call a leap technology,
Using extremely fine electrical connections. Instead of treating the upper and lower pieces as completely separate chips with a handful of large connections between them, the goal is to create a very dense network of tiny vertical connections. Think of two cities separated by a river. A traditional connection might give you a few large bridges. That lets major roads cross from one city to the other, but the cities are still fundamentally separate. Logic folding wants something much closer to an enormous grid of small bridges. The two cities begin behaving almost like different neighborhoods of the same city. That distinction is critical. Traditional 3D integration already exists. Companies around the world have been stacking semiconductor components for years. Memory can be stacked. Chiplets can be connected. Logic and memory can be combined in advanced packaging. Three-dimensional integration is not a Huawei invention. The interesting part of logic folding is the level at which Huawei says it wants to divide the logic. Rather than simply putting one large functional block on top of another, the architecture tries to use the vertical dimension as part of the circuit's actual design space. A processor is no longer just a flat map. The designer can effectively ask, which gates should stay on this layer? Which should move above them? Which connections become shorter if we move them vertically? And how can the circuit be rearranged so that the most important signals travel less distance? That last question is the heart of the Tau concept. The objective is not merely stacking, it is reducing delay. And there is a technical reason the quality of the vertical connection matters so much. Huawei's updated paper introduces something it calls the gear ratio. In simple terms, the gear ratio compares the spacing of the hybrid bonding connections with the spacing of the chip's uppermost metal routing. Imagine two gears. If the teeth are dramatically different in spacing, they cannot interact smoothly. If their spacing is much closer, the two systems can mesh. The same basic intuition applies here. If the bonding connections between the two layers are too far apart compared with the chip's internal wiring, the designer cannot freely move small pieces of logic between the layers. The vertical connections are simply too sparse. Huawei's paper says the ratio needs to stay below 3 for more fine-grained optimization, with a ratio approaching 1, offering the architecture's strongest benefits. The Kirin 2026 implementation uses a hybrid bonding pitch of 1.5 microns. A micron is 1/1,000,000th of a meter. At everyday scale, that is microscopic. Inside a processor, however, 1.5 microns is enormous, compared with the dimensions of individual modern transistor structures. And that creates an interesting point. LogicFolding does not require Huawei to suddenly manufacture every transistor at 1.5 microns. The 1.5 micron figure refers to the spacing of the vertical bonding connections. The transistor itself remains part of the existing process technology. The trick is to change how those transistors are connected and arranged. That is why the architecture can potentially create gains even without a new lithography node. But getting two semiconductor wafers to behave like one continuous circuit is not trivial. Huawei chose wafer-to-wafer hybrid bonding rather than relying on sequential 3D processing.
3D packaging at scale. AMD's X3D CPUs are only the beginning. But what exactly is hybrid bonding?
The reason is a real manufacturing trade-off. C-trasic integration means building one active layer and then processing another layer on top of it. The problem is heat. Many semiconductor manufacturing steps require high temperatures. If you have already built sensitive devices underneath, exposing them to additional high-temperature processing can degrade their performance. Wafer-to-wafer hybrid bonding approaches the problem differently. The active layers can be fabricated separately and then bonded together. That does not eliminate manufacturing difficulty. It moves the difficulty. Now the industry has to worry about surface flatness, alignment, bonding defects, connection reliability, and yield. And there is a brutal difference between demonstrating a clever stack in a laboratory and manufacturing millions of them reliably. Huawei says it has crossed at least part of that gap. The Kirin 2026 data is where the story becomes much more interesting, because for once, we are not talking only about a future architecture. We have numbers, the 2031 promise. Let's separate the story into two columns. The first column is what Huawei says it has actually measured. The second is what Huawei says it hopes to achieve. Those two things should not be confused. Start with the measured results. Huawei's V2 Tau scaling law paper compares the Kirin 2026 with the previous Kirin 9030 Pro. Both are described as using the same underlying process node. The major difference is architectural. The older design uses a conventional planar arrangement. The newer design uses LogicFolding. According to the published data, transistor density rises from 155 million transistors per square millimeter to 238 million. That represents roughly a 55% increase. This is important because transistor density is one of the traditional ways people judge progress in semiconductor manufacturing. But Huawei did not achieve that increase by suddenly shrinking the transistor with a new lithography process. It changed how the logic was physically organized. Then there is power. At equivalent performance, Huawei reports a 41% reduction in power consumption. The comparison is especially interesting because the operating voltage falls from 1.1 volts on the reference Kirin 9030 Pro to 0.9 volts on the Kirin 2026 under the stated test conditions. Lower voltage can have an enormous effect on dynamic power because switching power is strongly related to voltage. The chip also shows a 37.5% reduction in die area. That is not a small optimization. If the measurements hold across production conditions, the implication is that Huawei managed to get substantially more computational circuitry into a substantially smaller physical footprint while reducing power at the same performance target. And then there is clock speed. Huawei reports that at the standard 1.1 volt supply condition, the CPU's high-performance core frequency rises from about 2.75 GHz on the Kirin 9030 Pro to approximately 3.1 GHz on the Kirin 2026. That is important because it gives us another clue about what LogicFolding is actually accomplishing. The system is not merely squeezing more transistors into a smaller space. It is attempting to reduce the delay in the connections between them. If the critical path becomes shorter and electrically easier to drive, the processor can potentially operate at a higher frequency. This is exactly where the Tau argument becomes technically interesting. Huawei is effectively saying the transistor did not have to become dramatically smaller for the circuit to become more efficient. The layout changed, the distances changed, the interconnects changed, the architecture changed, and the measured chip changed with them. That part deserves to be taken seriously. But now we have to draw a hard line. Because Huawei's future roadmap is not the same thing as the Kirin 2026 measurements. Huawei says that by 2031, it wants hybrid bonding pitch below 1 micron. It wants alignment accuracy within 0.5 microns. It has a target of approximately 5 GHz clock speeds, and it projects transistor density equivalent to a 1.4 nanometer class process. Those are Huawei's stated targets. They are not independently verified 2031 results. There is no 2031 production chip sitting on a reviewer's desk today. There is no independent laboratory measurement proving that Huawei can achieve 5 GHz in a fanless smartphone processor using this approach.
Sustained 5 GHz performance in a mobile class chip.
And there is no basis for treating 1.4 nanometer equivalent as proof that Huawei has literally built a conventional 1.4 nanometer transistor. That distinction matters enormously. Modern process node names are not simply ruler measurements of transistor gates. When a company describes something as 1.4 nanometer equivalent, the relevant comparison here is primarily transistor density. Huawei is saying that its architecture could eventually pack transistors at a density comparable to a process marketed in that class. It is not saying that every transistor has a physical dimension of 1.4 nanometers. This is similar to saying that two buildings have the same floor space density. It does not mean they were constructed using the same materials or the same architecture. The comparison can be useful, but it is not identical to actually manufacturing on that process node. And there is another reason to be cautious. A scaling law is not really proven by one successful generation. If Huawei wants Tau scaling law to become a genuine replacement for the industry's traditional scaling model, it needs to demonstrate that the relationship continues. One generation could be a clever optimization. Several generations would begin to look like a repeatable engineering methodology. And several generations across different products would be much stronger evidence. That is why the roadmap matters. Not because we should believe it, because we can eventually test it. Huawei says future flagship Kirin processors will expand LogicFolding, with the approach eventually moving into Ascend AI processors and larger computing systems. That is where the experiment gets much harder. A smartphone chip is one thing, an AI accelerator is another. And the hardest problem may have nothing to do with transistor density. It may be heat. Why 3D chips are so difficult? Imagine a smartphone processor as a tiny apartment building. Now put twice as many residents inside without making the building much larger. At first, it sounds like a triumph of architecture, but then everyone starts cooking dinner at the same time. The building gets hot, and there is only so much heat you can push through the walls. That is the fundamental problem with dense 3D logic. Heat does not care how elegant your architecture is. A transistor that switches consumes energy. Some of that energy ultimately becomes heat, and a stacked chip can put more active circuitry into a smaller physical footprint. That can make heat removal more difficult. This is particularly serious in a fanless smartphone. A desktop processor can use a large heatsink. A server accelerator can use massive cooling systems. An AI data center can move enormous quantities of air or liquid across the hardware. A smartphone cannot. It has a few millimeters of thermal material, a metal frame, a small vapor chamber, or similar cooling structure, and then the outside world. That makes thermal density a critical constraint. Huawei's reported Kirin 2026 data includes a reduction in power density, which is encouraging. But that does not mean the general 3D thermal problem has disappeared. It means this particular implementation has produced favorable measured results under the reported conditions. The next generations are the real test, because if Huawei keeps increasing transistor density, stacking additional active layers, increasing clock frequency, and moving toward larger AI processors, the heat problem becomes harder. A 5 GHz target sounds exciting, but frequency alone does not create useful performance. The chip has to maintain that frequency without consuming excessive power or throttling because of temperature. And that brings us to another problem. Yield. Yield is simply the percentage of manufactured chips that actually work well enough to sell. On a conventional wafer, engineers already fight tiny defects. Now imagine taking two wafers and aligning them with microscopic precision. Every vertical connection has to land where it is supposed to land. The surfaces have to be extraordinarily clean and flat. The bonding has to be mechanically reliable. Electrical connections have to work. and the resulting stack has to survive manufacturing, testing, packaging, temperature changes, and years of operation. This is especially difficult because logic is less forgiving than some memory structures. If one unique connection inside a critical piece of logic fails, you cannot necessarily route around it. A defect can kill the entire chip. Wafer-to-wafer processing does offer potential advantages because two wafers can be manufactured separately and then bonded. But it also creates a difficult yield equation. If wafer A has a certain probability of being good and wafer B has another probability, the final stack depends on both. As integration becomes more complex, manufacturing discipline becomes increasingly important. And that is why Huawei's 1.5 micron bonding pitch is significant. The company does not need to immediately achieve sub-micron bonding to prove that the architecture can work. But if the entire argument depends on making the vertical connection network progressively denser, then future generations will have to become much more precise. Huawei's stated target is below 1 micron, with alignment accuracy within 0.5 microns. Again, those are targets, not demonstrated production results. The gear ratio is important here as well. If the bonding pitch remains too coarse relative to the chip's metal routing, engineers cannot freely fold the logic. They have to make larger decisions about which blocks go on which layer. That starts looking more like traditional 3D stacking. The closer the bonding pitch gets to the chip's routing pitch, the more the two layers can behave as one continuous design space. That is the promise. But it is also the trap. The more finely you want to connect the layers, the harder manufacturing becomes. Better alignment, cleaner surfaces, smaller defects, higher yield, greater process control. The architecture creates a feedback loop. To get the biggest architectural advantage, Huawei needs finer connections. To get finer connections, Huawei needs better manufacturing. And better manufacturing is exactly the problem the company has been trying to work around. Then there is the phrase 1.4 nanometer equivalent. This deserves one more clarification. A process node is not a simple statement that every physical feature is that many nanometers wide. Modern semiconductor naming has evolved into a broader technology generation label.
Semiconductor. In subsequent phases, this and other process steps are repeated until the entire layout of the chip has been deposited on the wafer.
So density equivalence can be useful for comparison, but it should never be translated into Huawei has built a literal 1.4 nanometer transistor. That is not what the claim means. Huawei is effectively proposing another way to obtain some of the system-level benefits traditionally associated with geometric scaling. More transistors in less area, shorter critical connections, potentially lower power, potentially higher frequency, without requiring the entire transistor manufacturing stack to advance at exactly the same pace. That is a legitimate engineering strategy, but it does not make physics disappear. And it certainly does not make manufacturing disappear. The real question is whether Huawei can continue doing this while keeping thermals, yield, reliability, cost, and design complexity under control. Because the moment LogicFolding leaves the smartphone and enters AI accelerators, the scale of the problem changes. And that is where the wider industry becomes very interesting. Huawei's biggest chip gamble. Huawei is not alone in moving toward three-dimensional computing. This is important because it changes the story. This is not simply China inventing a completely new category while everyone else sits still. TSMC, Intel, AMD, and other major semiconductor companies are already pursuing advanced packaging, chiplets, 3D integration, backside technologies, and other methods of improving how transistors and interconnects are organized. The industry has already recognized something fundamental. The future of computing is not going to depend only on making the transistor smaller. The package matters. The interconnect matters. The architecture matters. The software matters. And increasingly, the distance that data has to travel matters. Huawei's Tau scaling law is interesting because it tries to turn that observation into a systematic framework. Instead of saying transistors must keep shrinking, Huawei is essentially asking, what if the thing we really care about is reducing the total time required to move information through the system? That is a much broader question, and it could apply far beyond smartphones. Huawei says the LogicFolding approach is expected to move from upcoming Kirin processors toward Ascend AI processors, and eventually larger data center systems. That transition would be the real stress test. An AI accelerator contains enormous amounts of computation and data movement. If LogicFolding can reduce the distance between critical pieces of logic while maintaining acceptable power and thermal behavior, the potential benefit could be much larger than it is in a smartphone. But the opposite is also possible. AI accelerators produce far more heat. They operate at much higher sustained workloads. They require massive memory bandwidth. They have demanding packaging requirements. And the economics are brutal. A technique that works beautifully on a smartphone processor may not automatically work on a huge accelerator. The physical dimensions change. The thermal environment changes. The manufacturing yield equation changes, the software stack changes, and the cost of failure becomes enormous. That is why the next few generations of Huawei silicon will matter more than the 2031 headline. If the company can repeat the density and efficiency gains across multiple generations, while improving bonding precision and keeping temperatures under control, then Tau scaling law begins to look much more consequential. If the gains flatten out after 1 or 2 generations, the industry will probably view LogicFolding differently. Not as a new law of semiconductor scaling, but as another powerful design technique in the post-Moore toolbox. And there is something else to watch. Can Huawei make the vertical design space easy enough for engineers to use? Because designing a 3D chip is not simply designing a 2D chip and then rotating it 90 degrees. The electronic design automation tools, the software engineers use to turn circuit descriptions into physical layouts, have to understand the third dimension. The routing algorithms have to understand vertical connections. Timing analysis has to understand new signal paths. Thermal models have to account for stacked active layers. Manufacturing constraints have to be built into the design process. In other words, LogicFolding is not one invention. It is an entire chain. New physical layouts, new bonding technology, new design tools, new manufacturing processes, new testing methods, and new ways of thinking about what a chip actually is. That is why the Tau scaling law announcement deserves attention, even if the most spectacular roadmap claims never arrive. The interesting part is not the phrase 1.4 nanometer. It is the possibility that transistor scaling could become less about one number and more about a combination of geometry, interconnect, architecture, and time. The semiconductor industry spent decades making the switches smaller. Now it is increasingly asking how to make the entire machine behave as though everything were closer together. Huawei is pushing that idea aggressively because it has a particularly strong incentive to do so. The company cannot simply depend on having unlimited access to every leading-edge manufacturing tool. So it is trying to squeeze more performance out of the technology it can build. That is where the geopolitical timing becomes relevant, but only as context. The Tau announcement arrived during another period of intense US-China technology tension, around the time of renewed attention to the Trump-Xi relationship, and alongside Huawei's efforts to expand production of its Ascend AI processors, as Chinese companies were being encouraged to reduce reliance on NVIDIA hardware. The technology race therefore gives Huawei's research an obvious strategic importance, but the physics does not care about politics. A LogicFolding connection either works or it doesn't. A chip either stays within its thermal envelope or it throttles. A wafer either produces acceptable yield or it becomes too expensive. A 5 GHz target either becomes a reliable product or it remains a line in a roadmap. And that is why the most interesting part of Huawei's announcement may not be what the company says will happen in 2031. It is what happens next. The Kirin 2026 results give Huawei a starting point. The 238 million transistors per square millimeter give us a density measurement. The 41% lower power at equivalent performance gives us an efficiency measurement. The 37.5% smaller die gives us an area measurement. The 3.1 GHz result gives us a frequency measurement. Those are concrete. The future targets are different. Sub-1 micron bonding, 0.5 micron alignment, 5 GHz, 1.4 nanometer equivalent density. Those are bets. And now the industry has 5 years to find out whether those bets survive contact with silicon. The next revolution in chips may not come from making transistors smaller, but from changing how they live together. Huawei's LogicFolding is betting that distance, delay, and architecture could become just as important as transistor size. The Kirin 2026 results are promising. Higher density, lower power, a smaller die, and faster clocks. But the real test is still ahead. Can Huawei push bonding below 1 micron, reach 5 GHz, control heat, maintain yield, and scale this technology into AI processors? If it succeeds, Moore's law may not disappear. It may simply evolve, and the next era of computing could be built not just smaller, but vertically.